everyone, I'm super excited to be presenting a new style for the Weaviate Podcast. In this podcast episode, we have the authors of the paper, Yi-Lin Sung, Jaemin Cho, and Professor Mohit Bansal, a research team from the University of North Carolina at Chapel Hill, to explain this paper, VL Adapter, Parameter Efficient Transfer Learning for Vision and Language Tasks. And the reason this paper stood out to me as being so interesting is you see how this bullet point right here with the highlighted green text, you only need to update about 4% of the parameters of clip when you're fine-tuning it for downstream tasks. So you don't have to have the cost, storage overhead of fine-tuning the full 100% of a pre-trained clip model. Rather, you only need to have 4% of the updated parameters, which are added in these sparse adapter layers that are interleaved with the original model architecture. So this podcast will completely get into the details of exactly how these authors set up these experiments for having these sparse layers that you use to fine-tune something like a pre-trained clip checkpoint for different vision and language downstream tasks. And that's another really interesting detail about this is exploring exactly what vision and language datasets the authors were using to explore these questions. So this paper was accepted into CVPR 2022. It's a really great read. I highly recommend it. And I really hope you enjoy this podcast breaking down the details of the VL Adapter paper. So quickly before getting into the details of the podcast, I also wanted to point you to some examples of using clip within the Weaviate examples. So in case people out there aren't familiar with this, if you go to GitHub Semi-Technologies/Weaviate examples, and please leave a star while you're at it, you can see all these great examples of things that people have built with Weaviate. You see searching through podcasts, searching through plant information, Harry Potter question answering, and in this quick little example, I want to show you this clip multimodal text image search example. So within this clip multimodal text image search, you see how you can build a user interface for having your text to image search through using this pre-trained clip model. So hopefully this kind of seeing this in action and seeing how you can use this will further motivate your interest in VL Adapter and knowing that you could, fine-tune a clip, add that fine-tuned model into Weaviate, and then you can do this kind of text to image search. And it's very exciting, I think, having this multimodal image and text space, I think is really something novel. You see when Weaviate, as you're setting up your Docker Compose file, you can go down to, say, clip as the model that you want to vectorize your data. Hey, everyone. Thank you so much for checking out the Weaviate Podcast. I'm super excited to be welcoming a research team from the University of North Carolina. Their recent paper, V&L Adapter, is such an exciting finding with the clip model. The clip contrastive language image pre-training model is such an exciting model for producing embeddings of both images as well as text and having this vision language cross-modal, multimodal kind of crossover. And it's one of the most exciting examples of this is the clip model. It's built into the Weaviate backend for something that you can vectorize your input data. It's available with Gina AI's Clip as a Service. And it's been such an exciting thing to play around with generally the clip software. And I'm so excited to learn about this VL adapter. It's a strategy to only have to fine tune about 4% of the parameters of clip. So as we talk about taking this off-the-shelf pre-trained model and then using it in the typical kind of transfer learning flow, as we're similar with things like Hugging Face, where you take these pre-trained weights and then fine-tune them on your data set. This new advancement in VL Adapter is going to be huge for the cost implications of doing this and trying to fine-tune the massive model. So first of all, team, thank you so much for coming on this podcast.
Thanks for inviting.
Yeah, thanks for having us.
Thanks for having us.
And so can you tell us about if you had to explain VL Adapter sort of as fast as possible, how would you?
So VL Adapter is just a work that we want to adapt the existing language model, a combination of language model and vision model to vision language task with the minimum parameters use possible. So yeah, and we just want those added parameters, learn vision language representations, but the rest of them still keep the same as before. So yeah, it kind of brings a new paradigm that how to design the vision language architecture. That you don't have to fine tune whole parameters. You just only have to add several parameters and tune those parameters, and you can achieve everything. Could be exciting.
So can you tell me a little bit more about what kind of added layers you were putting in the middle of these models? Is it just say like a MLP dense layer in between layers 6 and 7, or is it a say normalization layer where you have the scale and shift parameters? How exactly is the model surgery being done as you add in these new weights for the fine tuning?
Yeah, so the layers we add is called adapter layer, and the architecture we've tried several architectures. So like the typical adapter is actually just like a two fully connected layers, and the two layers form a bottleneck structure. So the hidden dimension. So the input and fit to the first layer, and then there's a hidden dimension, hidden representation, and then the other layer will output the final representation. And the hidden representation is smaller than the input, so it's a bottleneck structure. And this is actually a typical structure of adapter. But we also try several other variations, like compactor that can use like low rank approximation to decompose the sum of the linear weights to like smaller weights to save efficiency, something.
Yeah, to give a little more like detail about adapter, and who's not familiar with like vision language pre-training, so there's recently a burst of like a vision language BERT, including like a VLBERT, LaxBERT, VLT5, VLBERT, and so on, where they combine the pre-trained language model with some vision encoder adaptation, and most of the previous models jointly fine-tune both all the entire language model and recently the adapter that are from the NLP field, and they only insert the specific feedforward network that is, as Yi-Lin mentioned, like a bottleneck structure at each transformer blocks. And we also follow that adapter layer and explore how it works for visual language.
So I think there's kind of two things in that I quickly want to unpack. And the first thing for Yi-Lin, can you tell me, so this compression bottleneck, the idea of the adapter as well as the low rank factorization is, say the intermediate dimension of the representation is 1024, you're going to compress it into say 256 and then blow it back into 1024 to put it back into the model. Did you maybe like ablate that detail? Is that detail important for making this work in general?
It's not that important, but one very important signal is that the bottleneck dimension is better than smaller than the input dimension. It can be like, so for example, if your input dimension is 100, that usually the hidden dimension, you can either work with 30, 50, 70, they all works. But if you put it as 100 or more than 100, it probably won't work. So so any number smaller than the input dimension will work. So not super important, but good to know.
Yeah, I think that's an interesting detail too, is the compression bottlenecks. I found that is like a good way to train neural networks, whether it's autoencoders or general that kind of thing. And maybe we could talk a little bit quickly about this strategy in transformers where you say mask out the CLS token representation. So it doesn't have the traditional kind of compression bottleneck that convolutional neural networks had, but you have that kind of indexing, and then maybe you have a compression bottleneck in that. Just curious if you have any thoughts on that kind of, say, isomorphic architecture, as they call it, and the kind of general use of compression bottlenecks in deep neural networks.
I actually do not have too much intuition on why this would, like, the compression bottleneck will work better. Because if you see in the transformer block, there's a feed-forward layers, right? And they actually use the inverted like bottleneck block, so the hidden dimension is bigger. So I think like sometimes it needs bigger, but sometimes it needs smaller. It's maybe like confused. I'm not really sure like why this would work, not why this happened. I think all I know is like empirically, adapter only works for like smaller dimension.
Yeah, I think it kind of comes back to like the categorical embeddings, the way it can like blow up the intermediate representation space. And say you have like the vector quantized variational autoencoder, or the GANs, the way that they can take these big latent spaces, compress them all the way into discrete bottlenecks, and then blow back up the latent space. I generally just think this kind of like the compression of it is so interesting generally.
Right.
And so another question I had for Jamin with what you said is, so there's two parts of the clip model. There's the ResNet image half, and then there's, say, the BART decoder half. Can you tell me a little more about that encoder decoder of the BART architecture, as well as the ResNet and like the particular details for people looking to, really get their hands dirty with clip?
Okay, sure. Yeah. We use BART or any kinds of like a sequence language model. In our experiment, we use both BART and T5. So we extend the encoder of the original language model to multimodal encoder. Actually, that's following the VLT5 paper. So we concatenate the text tokens and also with the grid of clips visual features. So we linearize all the visual features and we concatenate with the text embeddings and feed all together to the BART or T5, so language encoder.
So so the BART encodes on a concatenation of what it's the original input of the text as well as the image representation, and then as it decodes, you slide that autoregressive mask, right? So it's like iteratively decoding with the causal mask, as they say, that left to right kind of structure.
Exactly. So in addition to adapter parameters, we also learn a very like light. I think of one fully connected layer between the clip embedding to the bars, the text embedding. So it
Mhm.
maps the visual features to the like word embedding space that bar to understand.
Super interesting. So another detail of this study that I was really interested in is the particular data sets that you're using to study vision and language. And maybe you could take me through the data sets quickly, and then I could tell you the one that really stood out to me as being particularly interesting.
Yeah, so actually we focus on like vision language tasks and also video language task, and mainly focus on like question answering and captioning. So for like vision language, I mean image text task, we try VQA, visual question answering, and GQA, also question answering data set, and NLVR, which is a visual reasoning task, and Coco captions, a captioning task. And for video language task, we try like two video question answering tasks and two video caption tasks. So the former two are for TVQA and how to QA, and the later are the TVC and YC2C, like caption tasks.
Super cool. So quickly before getting into the data set I previously said it was my favorite, could you tell me a little bit more about the visual question answering? Is mostly common sense? Is it like counting tasks, like how many apples are in this picture, or what color is the apple, or what kind of questions is it being tasked with?
There's all kinds of questions actually in this. So the counting problems actually, yeah, there are some counting problem, and there are also some like yes no questions. The most of the data are yes no questions. Like is the person's shirt, the shirt on the man is blue or something like this kind of problem. And there are also some open questions like maybe ask what this person doing, what the man at the left doing, something like this kind of open uh, answer question. Yeah, but most of them are yes no question, and some other are numbers like you said, the counting question, and the other are open ended questions.
Yeah. To give a little
Because
more context about the dataset creation, we chose a four task VQA, GQA, NLVR, and the Coco caption to cover the diverse aspects of different visual language tasks. As you know, Coco caption is naturally generative task, and the visual reasoning NLVR is a like binary classification test, like if the visual input and the language correspond or not. And the
Yeah,
VQA,
more like an entailment task,
exactly.
Connor. Like basically, where you're given two or three images, and the sentence will either be entailed by only one of the images or all the images. So it's a multi-image plus text entailment reasoning task.
that's super interesting, and it also kind of facilitates the how you have your output space, right? Because if you just have 0, 1, and entailment, not entailment, or neutral, like three labels with neutral, also it's a lot easier than having the text generation kind of supervision, right? With how you kind of
Mhm.
get the signal back, how well you did on doing the task.
Yeah, I mean that's the good part why we used. And sorry to interrupt you, Jamin, so you can continue, but I'll finish this intermediate answer. Is that Connor? So you brought up a good point. Like we basically the whole idea of using VLT5, which was Jamin's ICML paper last year, was this whole motivation that can we build a sort of uniform model, right, that can handle yes no questions plus bounding box ID selection versus captioning, right, versus entailment. So can there be a unified sort of visual encoder plus textual encoder plus textual decoder kind of combination that can generate answers, IDs, answers, captions for all these tasks in the same model? So that's why we've used ClipBart and ClipT5 based on Jamin's previous work as the foundation of this adapter paper, right? The CVPR one we're talking about. But in the camera ready version for CVPR, you'll see on archive 2 that Yi-Lin and Jamin added another model, which is ClipWill, which is at ICLR this year. And that was to show that you can also get very good parameter efficiency and close to the full fine-tuning performance, even when using state-of-the-art discriminative vision and language models like ClipWill, which maybe Jamin, after finishing the dataset, thought you can also mention the ClipWill part briefly. Thanks.
We talk about NLVR captioning and the other the VQA, GQA, which Yi-Lin just covered. Like VQA, GQA consists of like different types of questions: yes, no, counting, spatial understanding, and so on. And yeah, I think GQA came a little after the VQA, which tries to address the computationality of the vision language task. So I guess the questions are generated by rule-based compositions.
Yeah, and that's my favorite data set pick. The compositional generalization thing has to be the most interesting. Well, it could be a pick for your most interesting thing going on right now. So, what do you think about the NLVR data set and the way that you can, really isolate this idea of discrete atoms that define the environments, and then test novel compositions of the discrete atoms, and this kind of symbolic logic of how you put together the environments to generate the vision language task?
So
Oh,
maybe
okay.
I think Connor is asking like if you have some more thoughts on GQA and its compositional challenges.
Yes. Sorry about
No
that.
worries.
Yeah, as you mentioned, like I believe such a compositional data set is really hard to solve with a like with the recent trend of like increasing the model size and parameters, because that compositional questions like recent like large models like compositional questions are hard to tackle where there's a like data set shortcut in the reasoning process. So if there's a statistical like biases in the data sets, a model will pick the questions based on the some sort like for example, if there's a few questions like how many giraffes are in the images, and there are only the images but one giraffe in the whole data set, and the model will not count the giraffe, but it will directly memorize the relationship between the giraffe and the answer one. So it just blindfoldedly answers zero. So we might need a fundamentally different like data set or model approach to tackle those such a, like compositional questions.
Do you think that's related to, say, it's overfit to the background or the texture of the clothing or whatever the thing is? Do you think you can have, say, data augmentation that kind of disentangles the correlation from the causation of what is supposed to be causing the prediction of, bird, deer, truck, and these kind of data sets? Do you think that kind of like causal inference is a way to think about improving that? And do you think data augmentation is maybe, a promising interface for adding that kind of causal bias to images particularly?
I think those are promising direction. I'm not sure they're the only directions. Like, uh, the both the causal like inference, causal modeling and the data augmentation have various like uh, things are similar, where they try to smooth out the statistical distribution holes. So but if we try to tackle the real world data set, there's much more aspects and combinations to cover. Like we need to combine the different backgrounds and different objects and different types of questions, different kinds of answers, and all these combinations can easily go to exponential. Yeah. So I think we need to figure out how to make this data augmentation much more efficiently.
And it reminds me of another paper I read from Professor Bonsel's lab is EnvEdit. It's a way to randomize the domains for vision and language navigation. And so it's kind of like this idea you've just described, the automatic domain randomization. It was used with OpenAI's Rubik's Cube, the way that they had their physics simulator, and then they also had visual conditions. And so they randomized all the environment parameters and tried to cover the whole distribution, that kind of philosophy that, we can use data augmentation, or we can construct a massive data set such that we cover all the distribution. Do you think that idea is, looking still promising, or like something that is feasible?
It might be an unpopular opinion, but I believe like making the more like great simulator is a way to go for the learning more a realistic data set. Of course, it requires like really great like 3D engineers, but to deal with the real world, we cannot really collect all possible images, and not only because of the data set creation, but it also deals with copyright and ethical issues. So I strongly want like if there's a like good game AI engine for AI.
Yeah, I think that's a fantastic direction as well. The Unity environments for vision and language, and the compositional questions of vision language, particularly because of how you can control that kind of thing. And So generally on this topic of multimodal learning, is this
Yeah,
something that
maybe
you're
Connor,
all?
I can briefly mention also something about EnvEdit since you brought it up. So yeah, so the idea there is more about sort of robustness and also making sure that the model is not overfitting or there's some strange background noise next to someone's
Oh,
microphone. Yeah, so basically, the idea there is more that you have to generalize to unseen rooms, right? So can the model sort of or the agent also do navigation in environments and objects and rooms and surroundings that it's not seen before? So the idea there from data augmentation or editing the environments is basically to make sure that the model is not overfitting to things that it's already seen, right? And it has sort of more
mhm.
regularization from that perspective, and hence creating different styles of the objects or changing the objects themselves, and also the style of the environments, right? These things can make sure, like you said, that the model is not latching on to certain sort of these uh, shortcut sort of features, right? Because now it cannot, like, it has to work in all these different variants too. So that's sort of like a different angle that that kind of work would need. But in terms of learning compositionality through data augmentation, I sort of agree with Jaimin that it's not that exciting in some sense to learn all possible combinations, right? And I mean, in some sense, it's a nice sort of balance between inductive learning and deductive learning, right? Like, is
Mhm.
it like showing a lot of examples and learning the rule from that versus being given a rule and generating examples from that? So there's a lot of work in compositionality in pure NLP tasks and papers too. Um, but the nice example of this simulation engine that Jaimin was referring to, you can see in his DALI eval paper that I don't know if you've followed, but with all this recent sort of discussion of OpenAI's new DALI model, we had this one of the first sort of text to image generation evaluation works, which
Mhm.
basically used Jaimin's and Abhay's simulator based evaluation paint skill dataset that has very fine grained control on what kinds of spatial relationships and counting and compositionality challenges to create in a dataset, such that you can actually test whether DALI is learning those specific relationships, or is it just sort of creating an average of everything that it's seen in the training data. Like, can it understand the chair left of the table versus the table right versus the chair right of the table, and so on, like all these different combinations.
Yeah, like a blue sphere on top of a red cube to the
Right,
net.
exactly.
Yeah, he's crazy. Yeah, I love that general thing of like generalization testing, robustness testing is a particular kind of it, a domain shift transfer, and kind of like this thing of studying these pre-trained models. Like on the Weaviate podcast here, we were about building these vector search engines where we put these pre-trained models as embedding providers and then build them into database indexes and then provide database services. So like we love this topic of kind of studying these pre-trained models. Do you think generally that's kind of an how do you think about that research direction where, say, for your new paper, you know, you're not even going to train a model, you're just going to take something off the shelf and then just design a suite of tests for it?
Yeah, I think that's where the this current sort of CVPR paper we are discussing, right? VR adapter makes some good sense, because as we start working or being presented with all these bigger and bigger models, and like you said, now you want to use those models, but for a different downstream task, you do not want to, and also most of the time will not be able to afford to sort of retrain or fully fine tune the whole huge model on your new task. So that's where I think this is the future, right? Where with just 4%, 1% kind of parameter updates, can you achieve almost the same performance as full fine tuning? And for more and more complex tasks that involve videos and language and images and so on. So to me, that's sort of the exciting connection between this paper and what you said. And then from the evaluation perspective, yeah, like as we were discussing DALI eval, I mean, that's sort of like a slightly different angle where instead of making these models sort of just bigger and bigger, and also being excited about how they look visually, this would be a more quantitative way to actually measure whether things got better at certain reasoning skills of spatial relations or counting or compositionality or biases. right? So it makes things more quantitative and also be able to compare to previous models and iterations. And I mean, eventually it would be even more exciting and fruitful to put these evaluations into the model training optimization process, right? So that while improving the model, while optimizing the model, you are trying to improve these metrics, right, as part of the optimization directly. But obviously, that will become extremely computationally heavy itself, which is again where things like parameter efficient methods come into picture. So that might be like one way to sort of uh, combine all of these things in and close the loop.
Yeah, that's a super interesting picture you paint. Like very complete with the idea of having you have the sparse fine tuning, it's cost effective, and then you have all these generalization tests that you can do during training, and maybe open source tools like weights and biases might be something that pops into people's minds as something that's creating these like massive log reports. We've seen a lot of papers in open source code, like maybe checklist and NLP, but yeah, this idea of having all sorts of logging and generalization testing and exploring all kinds of different kinds of behavior. So kind of wrapping up the podcast, our general goal with this one was to really hit the points and try to get the all the technical information as fast as possible. Kind of maybe wrapping up, maybe want to talk about like future plans or sort of that general topic of the code and what you plan on doing to take this kind of discovery further.
Yeah, my brief version, and then I'll let Yi-Lin and Jamin add more. Like I said, I think sort of my previous answer connects to this too. That hopefully being able to scale this parameter efficiency to newer, bigger models, but also especially in scenarios where you need maybe these kinds of evaluations as sort of part of the model in the loop. Um so that would be an interesting future direction. And also, I think Yi-Lin will probably mention about some future directions of VL adapter because the CVPR version focused more on multimodal vision and language models, but the adapters were still more effective on the language side. So there's still a lot of work left to be done in the community on how to make the adapters also more effective on the visual encoder side. Uh, so that's definitely one other future work.
Well, super cool. That's a super interesting direction to take it further. And I had so much fun learning more about the VL adapter. I think this is such a huge discovery. And I think just sort of the cost implications of this are absolutely massive that you can, only need to fine tune 4% of the full weights of clip to say fine tune it into your downstream task for whether you're working in e-commerce or you have some kind of creative idea for whatever it is with vision and language data sets. So thank you all so much for coming on the Weaviate podcast. I really enjoyed hearing the story of this paper and all sorts of details about this.
Thanks for having us
Thanks.
again.
Yeah, thank you.